Studies of heat engines led to the discovery of a state function called entropy. Okay, and this is a rather involved process of going from measurements of heat to the idea of entropy, and that's gonna uh, uh, how you get from studies of heat engine to entropy. That's gonna have to wait until you get to a higher level course. But the idea was uh, studies of the heat engine and the discovery of the second law led to the notion that systems have a property called entropy. Okay? And the way you can calculate entropy from heat measurements is as follows. If there's a change in temperature at constant pressure, there's no chemical change or no phase change, the only thing happening to your systems is temperature has changed, then the change in entropy is calculated by this formula right here. Okay, so delta S, change in entropy, is heat capacity times natural log of T final over T initial. Okay, now if heat flows at constant pressure, like if there's a, let's say you're melting at 0 degrees Celsius or boiling water at 100 degrees Celsius, if there's a heat flow at constant pressure and temperature, okay, this is temperature and pressure, okay, then delta S will just be Q over T. But Q is going to be equal to delta H at constant pressure, so you can calculate delta S from delta H. So delta S is going to be delta H divided by T for a process that's happening at constant temperature and pressure. Like when you're vaporizing water at 100 degrees, constant pressure of 1 atmosphere, constant temperature of 373 Kelvin, your delta S will just be delta H over T. Now for chemical reactions, you can calculate delta S. It's just the entropy of the products minus the entropy of the reactants. And we're going to talk a little bit more about that when we get to the third law of thermodynamics. Okay? All right, so let's use those equations to answer this question. What would be the entropy change when 5 grams of water is heated from 25 degrees to 100 degrees Celsius? What's our formula for delta S? Heat capacity times natural log of T final over T initial. Okay? Think of this as delta of ln T. Okay? Because ln T final minus ln of T initial is ln of T final over T initial. Okay? So, so what would it be? What's the heat capacity of 5 grams of water? 5 grams times 4.18 joules per Kelvin per gram, okay, times natural log of, so that's your heat capacity right there, times natural log of, what's our final temperature? 100 degrees Celsius, but we have to do it in Kelvin, so 373 Kelvin. 25 degrees Celsius is how many kelvins? 298 Kelvin. Okay, so that's how you calculate your delta S. What's our delta S here? 5 times 4.18. 5 times 4.18 times natural log of, I'm sorry? I did? Oh, I'm sorry. Okay. Let me take the natural log. Let me say 373 first over 298. 373 divided by 298. Okay, and I take the natural log of that. So that's 0.224 times 4.18 times 5. That gives you 4.69, so 2 sig figs, since 5.0 is only 2 sig figs. So 4.7 joules per Kelvin. Notice the unit for entropy is an energy unit per temperature unit, joule per Kelvin. Okay? So that's the delta S. So that's very similar to calculation of Q, except instead of using delta T, you take delta of LMT. All right. How about this one? What would be the entropy change when 1.80 grams of ice is melted into liquid water at 0 degrees? Delta H of fusion is 6 kilojoules per mole. And if you remember, at constant temperature, constant pressure, your delta S will just be equal to delta H over T. So delta S in this case is, what's our delta H? 6.0 kilojoules per mole, but we don't have a mole. How many moles do we have? We don't know, but can we figure out how many moles we have from the mass? 1.80 grams of ice, that's grams of water. How do you change that to moles? 1 mole of water is how many grams? Molar mass, 18.02 grams. It's 6.02 times 123rd molecules. But we're looking, since we know the mass, we change mass to moles. So 18.02 grams. Grams cancel out. Divided by our temperature, and moles cancels out. What's our temperature? Divide by 0. You divide by 273.15 Kelvin. Since we only have 2 sig figs, 273 will be just fine. Okay? 0 degrees Celsius is 273 Kelvin. So that gives us delta S of, let's see, 1.8 divided by 18.02. That's the number of moles times 6 kilojoules per mole divided by 273. Okay, so that's 0.00219, 0.0022 kilojoules per Kelvin. Okay, or kilo is 1,000, right? So that's going to be 2.2 joules per Kelvin. So that would be the delta S. Okay, you got it? That's how you calculate the change in the entropy. What do you notice about entropy? As temperature increases, what happens to the entropy? Delta S is positive. What does a positive change mean? Entropy goes up or down? Final minus initial is positive, right? So this is S final minus S initial. So that means the entropy goes up when you heat something, right? When you melt something, its entropy goes up.